Assalamualaikum warahmatullahi wabarakatuh. My name is Nur ANISAH binti ISMAIL and I'm going to demo my final assignment of assembly. So here is the code that I've been coded in the Microsoft Visual Studio. Then I run the debugger. The console has opened. And I've been given the task to complete chapter 4 and chapter 7. So enter a number from the menu, enter number 1. So it shows us the submenu from chapter 4 and enter number 1 for data transfer instruction. Enter. So it will show us the move 0 extension instruction. Move 0 extension instruction is when we copy a smaller value into a larger destination, and will move 0 extension will extend the upper half with 0 bit, and the destination must be a register. CX is 16 bit while CX is 8 bit, therefore it needs to be extended. While move signs extension instruction will extend the upper half by bit 1. And then move to exchange instruction, where the exchange will happen either with EAX and EAX, or with AX and variable 1. And it will exchange the value of the register. But if we have two memory operand like exchange variant 1 and variable 2, it will be an error. And then enter a number from the menu. We enter number 2 for addition and subtraction. The addition and subtraction have the increment, decrement, add, subtract, or negate. So as here shows, the code variant 1 double width 4, variant 2 double width 6, and then XOR EAX EAX. When increment the variant 1, the 4 will be 5, and then move to EAX. Then decrement, it will be 4 back, and then we add the variant 2, which is double width 6, we add to EAX, and then subtract the 6 just now with number 4. So 6 minus 4 equals to 2. Then we negate the 2, and the result will be negative 2. Then we enter a number from the menu. Just now addition and subtraction, and then continue with data related operators and directive. Enter number 3, enter. Okay, and then we continue with data related operator and directive. It have offset operator, PTR, type, length of, size of, and label actually. It's not included in it. So for the offset example, offset it return the distance in byte of a label from the beginning of its enclosing segment, while PTR is not there. It override the default type of label, provide the flexibility to access part of a variable. While for the type operator, it return the size in bytes of a single element of a data declaration. While the length operator, it counts the number of elements in a single data declaration. And here, the result of the counter is +2. And the size operator return a value that is equivalent to multiplying length of by type. But actually, there's another one, label directive, where it assigns an alternate label name and type to an existing storage location, and label does not allocate any storage of its own. It removes the need for the PTR operator. So let's continue with the sub menu number 4. Enter a number. 4 is the indirect addressing. The indirect addressing or operand hold the address of a variable, usually an array or string, and it can be dereferenced. And like what was stated here, was shown here, it hold the variant 1, double width 4, and then move the array of EBX into EAX. The result is positive 4. And for the last submenu for chapter 4, enter a number 5, which is JMP and loop instruction. JMP is an unconditional jump to a label that is usually within the same procedure. And we have a loop instruction here to display all odd numbers from 1 to 99. When we move ECX to 50, and it will loop the display by the EX, 2 here will loop until it finish the counter here. Actually only one. Every time it loop, it will decrement the number of EAX there. And that's for JMP jump. Then we continue by enter the menu. We already have all the sub menu of chapter 4. Then we enter 6 to return to the main menu. And now we take a look on chapter 7. We enter number 2. Chapter 7 have 3 sub menu: shift rotate instruction, shift rotate application, and multiplication and division instruction. Shift left operand SHL instruction, the first subtopic under the shift and rotate instruction. So SHL instruction is also known as fast multiplication, where SHL instruction is the instruction where it performs a logical left shift on the destination operand. The highest bit will be copied into the carry flag, meanwhile the lowest bit will assign with a 0. So here we can see the code written. This is the syntax SHL destination count. When we move DL, when we move 5 into the DL, and then we shift left DL by 2. These 2, we can fast multiplication by 2 to the power of 2 equals to 4. So 5 times 4 equal to 20. The SHR instruction is the shift right instruction known as fast division. It's the same way with fast multiplication, but it divide. Let's say we move the DL with 40 and then we shift to the right for 1. This one, 2 to the power of 1 equal to 2. So 40 divided by 2 equals to 20. Then shift right, another one more time, 2. 2 to the power of 2, 4. So this 20 we divide by 4, we get 5. And next is SAL, shift arithmetic left, A equivalent to shift left just now, and SAR, shift arithmetic right, is equivalent with SHR instruction. The SAR is identical to SHR, but the difference is the most significant bit is shifted back to itself because it is the sign bit. The ROL instruction, it shifts each bit to the left. The highest bit is copied into the carry flag and the lowest bit position. No bits are lost. For the ROR instruction, it shifts each bit to the right and copies the lowest bit into the carry flag and the highest bit position. In ROL also no bits lost. RCL instruction, rotate carry left instruction, shift each bit to the left and copies the carry flag to the least significant bit and copies the most significant bit into the carry flag, as shown in the code here, where the 88 hexadecimal equivalent to this binary value. For the first time, the CF carry flag is 0, and then this one bit will move into the carry flag for the first count. And then for the second, when RCL execute, it will another one time move the carry flag from 1. This one will move to the back, and then this one 0 bit will move into the carry flag. That is for RCL instruction. Continue with RCR instruction, rotate carry right. It just the same with RCL instruction, the way they operate, but it is in the reverse form, where the instruction shift each bit to the right and copies the carry flag into the most significant bit and copies the least significant bit into the carry flag. Next is SHLT instruction. There's so many S. SHLT syntax is shown: destination, source and count. Shift left double instruction, shift a destination operand a given number of bits to the left. The bit position opened up by the shift are filled by the most significant bits of the source operand. Only the destination is modified. If we can destination 9BA6 hexa, it changed to BA6AH after the source move this A into move according to this 4 bit. Meanwhile, for the SHRD instruction, shift right double instruction, it shifts a destination operand a given number of bits to the right, and the bit position opened up by the shift are filled by the least significant bits of the source operand. Next, we enter number 2 for the next subtopic of chapter 7, which is shift and rotate application. Here, I'm just put two things, multiplication and shifting multiple double word, because the one isolating string has been covered in the lecture. So I put shifting multiple double word. We already know that SHL, shift left, perform unsigned fast multiplication efficiently. So here, when we use the multiplication, the application of the shift and rotate, EAX times 20. Here, we can factor any binary number into the power of 2. And when we factor EAX times with 16, 16 is when 2 to the power of 4, and 4 when 2 to the power of 2. So it can be done this way, or it's more explicit to be seen in this form. Move EAX 1 to 3, and then move EAX into EBX. EAX is 5, 5, 2, SHL, 2 times 2. 2 to the power of 2 equals to 4, so 5 times 4. Oh, sorry, not 5, but 1, 2, 3 just now. Okay, then shifting multiple double word. Program sometimes need to shift all bits within an array, as one might when moving a bitmap graphic image from one screen location to another. The following shift an array 3 double word, 1 bit to the right. Here is the code. We continue with subtopic under the last subtopic of chapter 7, which is multiplication and division instruction. So multiplication instruction. Example 1, multiply 16-bit var 1 2000 hexa times with var 2 100 hexa. Here is the code. Var 1 is defined in the dot data and then dot code. Move AX var 1 200 hexa, move to the AX and multiply with var 2. When multiply, the answer will be 002000 hexa. It has overflow flag because the carry and overflow flag if is set if the upper half of the product is not equal to 0. Meanwhile, in the example 2, multiply EAX is just the same but only for 32 bits. Next, we go to DIV instruction. DIV instruction. The DIV instruction, unsigned divide instruction, perform 8-bit, 16-bit, and 32-bit unsigned integer division. The single register or memory operand is the divisor, and it has its own format where when the dividend is dx, so the remainder will be AH. When the dividend is AX, the remainder will be dx. And that's also I multiplication, IDIV, CBW, CWT, and CDQ. And those are the things that I'm not covered for the code. And then let's continue. So the last thing is we already put number 3 as the menu, or number 4. The number 4 will be to return back to the menu. Number 4 enter. Okay. Then exit. Just click 3. The program exited, and that's all from me. And thank you for my beloved lecturer, Dr. Farida.